Okay, so let's get started. I'm just in the community edition. And remember, you guys need to install the Magellan library. So yeah, if you weren't into yesterday, I think the coordinates are here, or the name and coordinates. Okay, so Magellan basically builds on Environmental Systems Research Institute, or ESRI's Java library. So I think this is kind of yeah, this article needs help. Okay, so anyway, this is their yeah. So these guys have done quite a lot of work in GIS and stuff, and so Magellan builds on it. The way it does that's nice is it makes sure that things are serializable and you can do distributed computing on these structures and so on. So we will just play with the primitive data structures and predicates very quickly, and then I will go through the actual data set in San Francisco, the Uber trips that Ram talks about in his 2015 and 2016 Spark Summit videos. This is before the New York City one. So, so I'm just creating an RDD of X and Y, pair of doubles there, and then I'm loading a Magellan point, and using a user-defined function that takes a pair X, Y of doubles into a Magellan point. Okay, so this basically is this way of doing it, and then if I I just create a new column, the with column method, and the name of the column is point, and then I'm using the 2-point UDF. So this takes in the pair of doubles and okay, so anyway, I think you were asking about the single quote thing. It looks like single quotes are used when you pass in arguments to a user-defined function.
Okay. Yeah, it's like a reference, maybe.
Yeah. So anyway, here's so the other way to do it is to use a built-in expression, and this is something DSL expressions in Magellan, and here I'm simply using this built-in expression point. And apparently this is much faster on larger data frames because it's doing some clever things, including code generation under the hood. So this morning I tried it out on the academic chart. So I wanted to just empirically verify if it's really slightly faster. I just did some random sequence of 10 numbers. I could just do -1 times next double and +1 times next double just to get a bunch of pairs of numbers. And I don't know, I'm just paranoid. I don't know if it's going to crash. Oh well, what the hell. Let's see, let's just do 1,000,000 points. 10 million crashed this morning on my other shard, which was running lots of jobs, so be careful. So this took like 2 seconds, and I don't know if this is going to take 1.9. Okay, I don't know. Maybe you can make this number bigger, but yeah, it seems to be slightly slower. So and then to sort of understand what SQL's Catalyst Optimizer does and how one can actually use this optimizer's methods to actually optimize your own custom data types. That's what Magellan is doing. Then you definitely want to get into this stuff. Right, so this is a sort of high-level blog about Catalyst and what it does. So Yeah. So, I mean, so at its very core, Catalyst contains a general library for representing trees and applying rules to manipulate them, right? So, so it essentially tries to, come up when you give a full-blown query, it comes up with the you know, the logical plan. It optimizes the logical plan, comes up with the physical plan, and optimizes and finally implements it, right? So there's a lot of processing that's going on under the hood before your query actually gets evaluated. So anyway, I let you guys look at this. This is actually one of those excellent resources. So if you want to understand what whole Stagecoach is, so so essentially at a high level, your entire operation gets converted to one massive Java function, and that's super optimized. And there's a big art and science behind this. Okay, I think this one, yeah, this one is a really good one too. What we did upstairs is kind of really silly. So if you want to do this a bit more tightly to really understand it, I think you should get into this notebook. So here we're, they're just doing a more formal way of doing benchmarks and testing how fast things are and things like that. So, yeah. So anyway, you can, if you want some more empirical evidence, you should get into that type of stuff. Okay. So now let's just create a Polygon data frame. So here I just have a case class, Polygon example. I import the Magellan Polygon, and then I have my array and called ring. And this array simply consists of point objects. This is the Magellan point objects. And remember from the video yesterday, Ram was saying that the convention in this field is to go counterclockwise. Okay. So when you write a polygon, you just put the points counterclockwise, and that's what's being done here. I just have this simple unit square, and then remember also from the video he was talking about how you can have a polygon within a polygon, or the data structures can be more general. You don't have to just have one polygon. Say a park in a map. So these are the primitives used to represent OpenStreetMaps, for example. You may have like, say, Pentagon. The US Pentagon will be a pentagon, and inside a little pentagon, right? So two things. So then you would just say the outer pentagon is starts from index 0. So in this case, there's only one ring, a square actually. So you'd say it says there's only one. It starts from index 0. Okay. But if you have two, then you basically will have array starting at 0 and array starting at, say, 4. So now I'm just just converting it to RDD using this case class, and then converting that to a data frame. So yeah, unfortunately, show will not show the details. Display somehow is broken from this new version of Databricks. Could have broken it. You don't see as many details as you do in the other Databricks notebook. So I want to try to fix that or get into it now. So predicates are the most primitive logical operations you would do once you have these data structures. You have points and polygons, and usually you're interested in, say, an intersection predicate. So I can, for example, do this as a join operation, points with column point. So I'm just creating my point method. I'm creating a column called point with my Magellan points using the built-in method. And then I'm now wanting to join with this other single row data frame, which is called Polygon. And then I'm interested in where the point intersects with the polygon. So I simply want to know if each point intersects with a single polygon. So this should give me 3, because if we look at the polygon is made of 1, 1 on the very top, and then 1, -1 and -1, -1, and -1, 0. So, and it goes back to 1, 1. So what are my points? My points are up here. Right, so my points were, yeah, -1, 1, -1, 1, sorry, -1, -1, -1, 1, and 1, -1. So it's the 3 corners of the square, right? So of course there's 3 intersection. The other predicate is asking whether it contains, I believe. Yeah, containment. Containment. Not sure if containment is E. So anyway, right. So we should get 0 because it's only on the boundary. It's not inside. Okay. So this is the within operator predicate. Now we can create lines from 2 points. Okay, so like that. And so here, what have I done? I have a case class called line example, and then I'm taking a line and just I need at least 2 points to create a line between those 2 points. And then I can create a polyline, which is going to be just a whole bunch of lines. And it can be a sequence of lines, as in this case. And I'm just saying, I'm just taking the same array ring, and I'm treating this as a line. And I'm saying, you know, the line index starts at 0. So there's only one line. So it's a polyline because it snakes around. So maps, OpenStreetMaps uses polylines. So it's called ways. Okay.
What is the difference between a polygon and a polyline?
So I guess Polygon would come and close on itself.
Okay, so polyline doesn't have to.
No.
Okay.
I think. I mean, I think so. Because remember, he was talking about these algorithm of finding whether a point is within a polygon or not. That assumes it's a closed thing.
Mm.
You know, because if you go northwards, you can odd number of intersections would be inside, and even number would be outside. Yes. Yeah. So just I really haven't read the docs for Magellan or Esri, so my only experience with this is, you know, I have a link to this video on the bottom. This student last year in New Zealand did a huge project where he was ingesting OpenStreetMap data, which is freely available in like Google Maps or Apple Maps, and using Magellan to represent very, very large OpenStreetMap data, like all of San Francisco or all of New Zealand. We could do it. And of course, that's really fundamental, because once you can use Magellan and get OpenStreetMaps that anyone can download, then for example, you can look at lat long of Twitter or whatever. You can ask people to ping you, so you suddenly have action. You have traffic information or whatever. So let's just so I'm just sort of displaying this. Oh, maybe I didn't run this command. So yeah, some of the displays partially work. So it just tells you like what's the bounding box for the lines. It says the x coordinates are 1, 1, -1. So it keeps the x and y coordinates separately. And, it's non-empty. And these things are of type 3, polygons are of type 5 or something. There's the various types. I don't know the exact conventions under the hood. So this is just another example. I just wanted to make 2, instead of having one long line, I just wanted to make 2 lines. So this just, it works. Just tested it. Okay, so that's pretty much all the primitives to load OpenStreetMaps, basically. So now we already did this. Victor Ingman.
Yes.
1N? Yeah. 2N.
No, 1. Correct.
Victor
with a K. No, not with a K.
Yeah, I think if you send me a published link to your notebook, then I can.
Yeah.
Okay. Okay, so this is good. So now let's just go back to this Uber thing, and you know, I can just sort of. So what? Once you have loaded it from downstairs, you'll just get this. And so if you look at the just the top 5 things, you have the trip IDs and the timestamps and the latitude and longitude. So this is just Uber. And if you look at it, the same trip ID, you know, this is 4 seconds later, 4 seconds. So it's like, yeah, it's every 4 seconds. You have a boom, boom, boom. That's very common type of spatiotemporal trajectory data. So then I'm sort of loading this legacy shapefile format. Remember, this is not the GeoJSON, which is more, I don't know if it's more modern. I think it is because it's just one file. This one's much more complicated. It's a directory with lots of different files, and they all encode something. Anyway, so watch this if you want to understand a bit more about. So we basically make a case class called UberRecord with the trip ID as string and timestamp as string and point as point. And all I'm doing is just reading the pure text file, doing a map where each line gets split by tab because it's a tab separated value file. And first, 0th, first, and third parts are basically third and yeah, and there's some bizarre swapping here. Long and lap are flipped. Okay, so then now I just wanted to actually do an action. So what is requested to be cached gets cached now. So we have what, 101.1 million records. So now I'm just loading this San Francisco neighborhood information like this, and I'm selecting, and there were 37 neighborhoods, and my schema. So it's very similar to your GeoJSON thing. It's different. So it's ingested, and then it looks like this. I have my Polygon and my metadata about it as a map, keys and values, and all the Polygon information is sort of shown in this object. It's quite a long polygon. Right? So here's my SQL functions because I wanted to use this explode command. So I'm just calling some SQL functions. And all I've done is exploded the metadata into 2 columns. So grab the metadata and then just converting the map into a sequence of key value pairs and then just showing all of them. So this gives me my neighborhoods, all of them. Soma, he talks about south of Market, San Francisco. Has anyone been to San Francisco?
Yeah.
Yeah. Okay, so so now let's do a join. This is just out of this video. I was just replicating it. It was quite difficult to replicate this. So Ivan actually helped me to figure out what was going on. See, I got here yesterday, and then I was like, okay, so let's do this. So there's this bit of code that comes later, and then unfortunately it wasn't working because Ram apparently removed this in this GitHub commit, and I don't know. There must be another way to do this transformation. I haven't figured it out. So Ivan just found this, and so I'm just pasting the code that was removed to replicate what the 2015 video was talking about. So this is, so anyway, this is this class, NAD83, which is a standard format. The Uber trips are in a GPS standard format, and NAD83 is the format the San Francisco's neighborhoods are. So we need to make sure that the projections onto the plane, there's two different projections, are matching. So we just have to do some arithmetic, okay? And
Ross,
yeah,
the command for the two work.
the command for which?
When you create the neighborhoods.
Yeah.
You get, it
doesn't work for you?
Yeah.
The communication. This one?
42.
Oh, command 42, right.
Yeah, and the
this
comment
one
might be busted. Or did you change something?
Oh yeah, this may be busted. Yeah, no, so now it's working for me.
Okay.
It's not for you?
No, it doesn't match in a file.
Oh, did you download all the stuff?
I've run the whole language up until this. So I have all the UberRecords.
Oh, what about San Francisco? So there's another wget below. See? This is the San Francisco wgets. So you want to go and this one.
Skip those.
Okay. Yeah, just do these, wget the neighborhoods and dump them in the right directory. So. Yeah, they probably have a GeoJSON version now too. I don't know. So anyway, but this I thought would be good anyway because you may want to roll your own transformations. So this could be useful later. We can add on to this. So yeah. So there's some implementations of NAD83 class and some zones, some specific maps for specific zones, 401 and 403. You can add more zones, and if you use a sort of GIS software, all of this will be built in for you, but it's nice to see what the arithmetic is. And then, yeah, there's even to Lambert conic projections and transverse Mercator projections from Lambert conic. I don't know. So this is all from Ram's stuff that he deleted, and I don't know what's the modern way of doing this, or the latest way of doing this, but we'll just do it in this old way so we can reproduce the problem he was trying to emphasize. So this is so now we have the NAD83 class upstairs, so we can essentially define a transformer which goes from one Magellan point to another Magellan point, and it's so it basically tells us what we need to do. This must be the San Francisco zone, I think. And so finally, once I have a transformer defined, I can simply define my Uber transformed from essentially the Uber by taking my NAD83 column to be my new column, where I simply take my point column and transform it with the transformer. It sounds like some movie. Do you guys know Transformer?
Yeah.
Good. Transformer. So there we go, just making sure that we have the same number of rows still. And if you just look at Uber transform show 5 false, now you see this new column with, you see the numbers are slightly different and it's in this other projection. And now we are back in business because the Uber data and the neighborhood data match now. Okay. So this tells us the unique trip ID. So we basically have 24,999 Uber trips, unique IDs. So there's, it's 4 seconds. So what was the total? So roughly, I mean, this is not the right thing, but just to give a rough idea of the mean of dot 0. It should give me. So that's the average number of events per trip. And of course, some trips may be very short and some may be long. I don't know if 4 seconds is standard for every trip. So. Okay, so let's try the join again after some appropriate transformation here. So it's exactly the same join, but now we are going to ask where the NAD83 column lies, if the NAD83 column lies within a polygon or not. And of course, the polygon is coming from the neighborhoods, and NAD83 is coming from the Uber transform data frame. And then once we've done the join, we're only going to select the trip ID, timestamp, and then we're going to explode the metadata, which comes from the neighborhoods column, and then as a key value sequence. And then we're going to have the value value column renamed as neighborhood, and we're going to drop k because we don't care, and cache it. So now we act. So what it's doing now is a broadcast hash join, right? Because then the Spark's catalyst, or it'll already figure out that one of the tables is much smaller than the other, right? The neighborhoods table. So it'll just it'll broadcast it to all the workers, and so they will all have a local copy. So they just are joining the other table, whatever rows they have there, against this. I really would have loved to get into the details of what Ram has been doing the last year or so. We'll come to the bottom of it, because now, so in 2016, he said he was going to use more interesting spatial data structures, like space filling curves, where you can basically take a 2-dimensional object and use a 1D curve to fill space. So this is like Hilbert space filling curve like things, but there's something called z-order curves and others. So he's using one of those already in the current version of Magellan. I haven't descended into it. And in fact, in the New York taxi thing, or in his blog, actually, he talks about how the speed improves heavily when he uses one of these spatial indexing data structures, right? So that's definitely worth playing around. So anyway, let's just see. So now we are done, right? So we have each trip ID with the timestamp mapped to the neighborhood that it falls in. So now this is just seeing how many trips don't fall into any of these San Francisco neighborhoods in our polygons, right? So these could be taxi trips that left official San Francisco neighborhoods, or it could be bugs that we don't know yet. But currently, it's a smallish number compared to the rest, so I think let's just ignore that. And so here I'm just doing a group by neighborhood, and I'm doing an aggregation on using this count distinct method. So I want to count the distinct trip IDs after I've aggregated by the neighborhood. So I will know how many distinct trips are in each neighborhood. And then I'm going to order it by the newly named column trips, which is in descending order and showing the top 5 neighborhoods. So basically 9,891 trips were in South of Market. So that's distinct trip IDs. So which is different than your New York one, right? Because this is not just the pickup point. This is actually, so if a trip started in South of Market and ended in South of Market, but say it went into, I don't know, one of the neighboring suburbs, then I think each suburb will get an increment of 1.
So they don't differentiate between just stop there, or if you just pass by.
Yeah, this query doesn't, right? This SQL query is just like, give me all the distinct trip IDs in each neighborhood. So, but you could do a lot more. In fact,
could like say if this neighborhood you always pass by, but you never stop here, and stuff like that.
Yeah. So yeah. So you can do quite a lot. So there is. I'll take you somewhere where you can really have fun if you want, where you formalize a slightly different, formally an algebra where you take time as an interval and do a Cartesian product with these points, which you can enlarge into a circle. Magellan already has those primitives. So then you basically have like time space balls, and so you can start doing more interesting things with that. So Dylan's notebooks go in that direction. I'll point you there. Yeah, so this is basically, so spatiotemporal queries can be expressed in SQL using Boolean predicates, like belongs to, intersection, and so on. So, but we can easily do space-time version of it. So we will have, say, a time interval t start and t end, and a polygon p. So we simply take the cross product of this. So now someone is somewhere at some time interval, right? So, and usually it makes sense to make the GPS coordinate into a ball because there's uncertainty with the measurement itself. So that'll be your sort of primitive enclosure of where you think someone is at a certain time. So I think this particular video, so if you start from 34 minutes onwards, it's the first student presentation of the Scalable Data Science course from Middle-earth from 2016. And George Dillon, he's now a data engineer in New Zealand. And what he did was he did a spatiotemporal taxi trajectory analysis using the Beijing taxi dataset from Microsoft Research, which is quite big. And he also did like map matching. So there was an open source map matching software where you take, say, OpenStreetMaps, and then you can sort of snap so you put like a whole bunch of GPS trajectories like Uber. That's kind of what you will get from a taxi provider or even a person, right? Because has anyone turned on your where am I? There's a Google thing you can turn on. It keeps track of all your location history. Anyone done it? No. You have? Yeah, a lot of people really like it because they're like, oh yeah, where was I? Especially the massive drinking hangover. And I was there as well. So anyway, it's again the same. So, but Google, because it has so much more resources, like, they would already do various things like map matching and whatever. They use probably even wireless information. So you can do map matching by simply snapping the GPS coordinate to the nearest roadway if you know that you're going on a road, if it's a taxi, for example. So it can improve the accuracy of your location heavily. So he was using some library, I think Graph-hopper, and then ingesting OpenStreetMaps in a very low-level way. But now Magellan already has a direct ingestion of OpenStreetMap data, so I haven't played with that either. So you can kind of see this here, and the notebooks are all in the stuff. Okay, so I think, so this is what I said. So Ram wanted to do more clever, spatially aware data structures to speed up the querying, and I think he's done it. I haven't really caught up with it. And these are some other things I thought were quite nice to read later. Okay, so let's continue. So we'll maybe just spend a little bit of time on LDA. And we can come back to LDA later. Because some of you wanted to do Mariama wanted to do some text-based project. So are there any questions up to now about? So we won't really have too much time to get into LDA, but I'll just start you off. So what you want to do is go downstairs, because this is going to take a while. You might as well get this out of the way. And yes. Yeah, so this is not quite true. Yeah. So so Databricks already has some data that's loaded for you. So if you know, this should work in the community edition. So what they've done here is given you a much simpler form of this 20 news group dataset, the sort of bread and butter of latent Dirichlet allocation. But I wanted to do the full thing because you might as well, and it's slightly more realistic. So just uncomment all of this and start pulling stuff down. This worked. And this thing will take like 12 minutes, so you might as well do that now. Get it over with. And it's taking a long time because I'm sort of loading a lot of small files into a distributed file store. It's not optimized for it, but we'll just do it anyway. But once it's loaded, then we can access it. Okay. So once it's loaded, you will see some mini news groups. There's various topics, atheism, computer graphics, and so on. And then we will basically, in the end, what we will be doing is something like this. So you'll be able to, you'll be able to essentially find topics in various posts, right? Without knowing what news groups these posts are coming from, you will be able to sort of find the topics of each post. And it is remarkably useful, which is so here's the summary. Our task is to identify topics from a collection of text documents. Right? So think about it like we are helping a digital historian, right? Because I think I mentioned earlier, there's this whole field called digital humanities that's exploding right now. And it's, again, because of this digital age we're in. If you want to be a historian of, say, Bill Clinton, you cannot do what you used to do when you were a historian of, Roosevelt, for example. Okay, it's a very different world because Clinton's scholars have to now, read lots and lots of emails, lots of digital communications. So it's just a lot of information. So the modern historian already should be well versed in programming and know a fair bit of stats and maths and so on. So we can think of this as something that a digital historian would do to help him or her make better sense of the documents. Because at the end of the day, this historian has to go and read the stuff and do proper history, right? So I'm definitely not saying we're going to build some kind of a sentiment detector that tells what you should read. I really don't, want to go into that kind of natural language processing. But this is quite useful generally. Okay, so our input will be vectors of word count. So we're doing something super simple. And this can be complicated beyond just word counts. We can work on bigrams or more, and even more complicated input vectors. Optimizers, we're going to try two. We may not get this far, but let's see. So one of them uses expectation maximization as its optimization routine. The other one uses another method called online variational base. And this uses something very similar to stochastic gradient descent. Okay, it uses iterative mini-batch sampling of the data. Okay, that's a very high-level outline of the inputs and the task and the algorithms. Here are the links to the API docs in Scala and Python. What we will be doing are feature extractors and transformers from the ML pipelines, and you know, you can try to get an idea for the details from Wikipedia on LDA. So if you're going to read one paper, let's see how this loads. Oh no. This paper is missing. Yeah, it's gone. So this is a really good paper. Let's see. Find it. Anyway, let's look at the other one. Yeah.
Is it?
Did you find it?
Is it this one?
Yeah, it's that one. So did you go to the ACM digital library and get it?
No, I googled the file name.
Oh, Google the file name.
Play.
That sounds like a good idea.
Yeah.
Oh, I see. Yeah, so someone has it in their GitHub. Let's see. It's a very good paper. Oh, it's in Colombia. Maybe you moved to Colombia. Yeah. Let's see. So, all right. So that's the. I mean, we won't have time, but read this. So let's just sort of quickly go through the idea. So yeah, it can be applied to massive collections of documents, and it's a generative model used to discover main themes in a large collection of documents. Right? And the other nice thing is it allows you to adapt the model to various kinds of data, and you can even have your own sort of you know, subjective insights thrown into it in a Bayesian way. So here's the main two-stage process for generating words. So we generate words in a two-stage process, right? It's this. So first we randomly choose a distribution over topics. So you say we have k topics, k is 10. So we first randomly choose a distribution over topics. And of course, these distributions are Dirichlet distributions. So that's why it's called latent Dirichlet allocation. Latent, it means it's hidden. Dirichlet means it's the generalization of the Bernoulli. You know, it's the generalization of a discrete distribution. So in say in K is 3, you basically have 3 topics. So you're looking at the simplex in 3 dimensions. You know, yeah, the Dirichlet distribution sits on that space of probability masses that sum to 1. Right? So for each word in the document, you do the following. You randomly choose a topic from the distribution over topics. And then you randomly choose a word from the corresponding distribution over the vocabulary. So these are the main ideas in the generation, and this picture quickly summarizes it. So we're definitely running out of time, so I'll stop. I strongly recommend you read this, and we'll come back. And we could maybe very briefly just make sure everyone is on track for their projects. You guys are interested in the security thing, maybe?
Yeah.
Okay, good. And do you have any idea what you?
Not yet, but I'm not sure if I'll be taking the second one.
Okay. Okay, that's good. Okay.
Yeah, I was going to say.
Okay, that's good. You're, yeah, dropping out. That's good. So are you thinking of taking this?
No, I'm taking the second part. Probably work with
Napster?
Maps.
Oh, maps. Okay, good. OpenStreetMaps or.
Okay.
Okay, cool. Okay, that's good.
Yeah, I think there was some genomics, maybe
Yeah.
scale.
Okay, good.
I will see, but there's the idea maybe to write a small package for Hail to do some.
That sounds
That is
good.
what it will have.
Yeah. There's also Adam. I don't know if you checked that out. It's from Berkeley. Adam for genomics. So they do a lot of PopGen stuff as well. I don't know if they're different or how similar. Okay, that's good. What about you?
I'm using those wearable devices.
Oh, wearable devices. Okay.
I haven't data yet, never simulations.
Okay. Okay, but these wearable devices are geolocated on maps and things as well, or?
I don't know yet. So it's some development, some pharmaceutical company.
Okay. Okay. Good. That's good. Do you think you might be taking?
I have no idea.
Well, do you think you might be taking the second?
I will definitely take it.
Yeah.
But I'm not sure if I will do this program.
Okay. Yeah. Okay.
It depends on the stress.
Yeah. Yes. That's good. Okay. No, it sounds good. I mean, if you're interested in like probability, and I don't know what exactly you're interested in, there is a lot of interesting research on very, very large scale simulations. So people are finding counterexamples to classical conjectures and things like this. So it could be, maybe. Okay, that's good. I think we have 1, 2, 3, 4. Yeah, 5. Yeah, and yeah, maybe at least 6. And Miriam might do. Okay, that's good. So I think if 6 people are there, I think it's probably worthwhile.
When does the second part begin?
So November 8th, right?
November 8th.
Yeah. So